Hello! We discussed tut sets last time, and we saw some of the structural information we can get on the graph based on the tut sets. For example, the vertices in the tut sets are all essential, and the even components after removing the tut sets all have perfect matchings. We will now discuss a special property about the odd components. For some tut sets, these odd components are what we call factor critical. And here is a definition. A graph G is factor critical if G minus V has a 1 factor for all vertices V. So G by itself does not have a 1 factor, but removing any vertex will give us a 1 factor. We make an easy observation that a factor critical graph has odd number of vertices. It is also connected, which is not as obvious, and we will ask you to explain why that is. Now, can you come up with some simple examples of some classes of graphs that are factor critical? We see that odd cycles are factor critical. We can find a matching that covers all but one vertex, and then rotate the matching so that each vertex could be exposed by a maximum matching. Another example would be the odd complete graphs. Removing any vertex gives us an even complete graph, which must have a perfect matching. But there are other examples too, and here are 2 of them. It is not entirely straightforward to show that these are factor critical, but later we will find a way to generate all possible factor critical graphs. Now it should be clear that in the factor critical graph, every vertex is avoidable. But the converse is also true, and that is our first result here. Let G be a connected graph. Then G is factor critical if and only if every vertex of G is avoidable. And here is our proof. In the forward direction, if G is factor critical, then G minus V has a 1 factor, which is a maximum matching in G that exposes V. So V is avoidable. In the other direction, we suppose that every vertex is avoidable. From this, can you say what is a tut set in this graph? We have a result that says that tut sets have essential vertices, but no vertex is essential, so empty set is the only tut set. So then, the deficiency of the graph G is equal to the deficiency of the empty set, which is the tut set. And this is just equal to the number of odd components of G. But G is connected, so the number of odd components is either 0 or 1. So why can't this be 0? If this is 0, then the deficiency of G is 0, so G has a 1 factor. So every vertex in G is essential, and that contradicts our assumption that every vertex is avoidable. So G must be an odd component, and the deficiency of G is 1. And by the Tut-Bear's formula, the size of a maximum matching in G is half of the number of vertices minus 1. Now remember that any vertex V is avoidable. So by definition, the size of a maximum matching in G minus V is the same as G. But that is the number of vertices in G minus V over 2. So that means that G minus V has a 1 factor. And that proves that G is factor critical. And that completes our proof. Now, one way of finding factor critical subgraphs in G is through the use of a maximal tut set. And here is our next result. If T is a maximal tut set in G, then every component of G minus T is factor critical. Now, the proof of this theorem is very similar to the last part of the proof of Tutt's theorem, so we will not repeat that here. Recall that in the proof, if T is a maximal Tutt set, then G minus T consists of only odd components. And by using similar arguments from the proof of Tutt's theorem, we can show that each of them is factor critical. And we will ask you to verify the details of this as an exercise. We will now discuss the structure of factor critical graphs. There is an interesting characterization of all possible factor critical graphs, and that is through the following definition. An odd closed-ear decomposition of G is a sequence of graphs G0 to Gk where G0 is a vertex in G. For any I between 0 and k minus 1, we can get Gi plus 1 from Gi by adding Pi, where Pi is either an ear of Gi of odd length or an odd cycle that intersects Gi at exactly one vertex. In other words, the intersection of the vertices of Pi and Gi is 1. These are the closed ears. And the last graph Gk is G. And here is an example of an odd closed-ear decomposition. We start with a vertex G0, add a closed odd ear P0, which is a cycle of length 5, and an odd ear P1, which has length 7, etc. And here is a theorem by Lovász. A graph G is factor critical if and only if G has an odd closed-ear decomposition. Now, the proof of this theorem is a bit technical, and it involves the idea of symmetric differences of two matchings. So here is an example of two matchings M1 and M2 inside a graph. Can you describe in general what does M1 delta M2 look like? In this case, we have some isolated vertices, a path, and a cycle of even length. And this is what we usually expect in the symmetric difference. And we will write that down as a proposition. Let M1, M2 be two matchings of G. Then, the symmetric difference of M1 and M2 has maximum degree 2. That is because each vertex is incident to at most one edge from each of the matchings. So this means that non-trivial components of M1 delta M2 are paths and even cycles. Moreover, the edges will alternate between M1 and M2 on these paths and cycles. We are now ready to start the proof of our theorem. We will start with the reverse direction. We assume that G has an odd closed-ear decomposition and show that G is factor critical. As we have seen many times before with ear decompositions, this would be a proof by induction, showing that each step of the way, the graph is factor critical. Now this involves some careful case analysis, and we will only give you a sketch of this. We could have a case where we are adding an odd ear, and depending on where the exposed vertex is supposed to be, we can find a matching that covers everything else. And similar when we add an odd cycle. We will leave the details of this case analysis as an exercise. In the other direction, we let G be a factor critical graph, and we want to build a closed odd ear decomposition for G. We'll start with G0, which consists of any vertex x in G. We let Mx be a one factor of G minus x, and this exists because G is factor critical. We will now inductively build Gi plus 1 from Gi by adding odd ears or cycles, while always maintaining an invariant. And this invariant is no edge of mx is ever in the cut induced by any v of gi. This is certainly true for g0, as there are no edge in mx that is incident with x. From here, we will assume that this invariant holds for gi, and after building gi plus 1, we need to check that the invariant still holds for gi plus 1. We first deal with two easy cases. If gi is equal to g, then we are done. In the second case, if there exists an edge that is not in gi, but both endpoints are in gi, then we can simply add this edge to gi to get gi plus 1. The invariant still holds for gi plus 1 because we did not add any edge from the cut induced by the vertices of gi to get gi plus 1. We now look at the case where gi needs to grow beyond its borders. We suppose that there exists an edge uv that is not in gi, where u is in gi but v is not. This edge exists because g is connected. And this is where we need to use the invariant, because that tells us that uv is not an edge in the matching mx. We now look at another matching. We let mv be a one factor of g minus v. So this is a matching that covers every vertex in G except for V. We will now consider the symmetric difference between mx and mv. Can you see what are the vertices of degree 1 in this symmetric difference? We see that x is covered by mv but not mx. mv is covered by mx but not mv, and all other vertices are covered by both. So the only vertices of degree 1 in mx delta mv are x and v. Using our proposition above, which says that this symmetric difference consists of paths and cycles, this means that v and x are the endpoints of a path in mx delta mv. And let's say this path is v0 to vm, where v0 is v and vm is x. We can see an ear forming on this path. We start with v0 that is outside of gi, and we let j be the smallest index such that vj is inside gi. So it is the first vertex that is in gi. And this exists because the last vertex, Vm, is in gi. Then, the edge Vj minus 1 Vj is in the cut induced by the vertices of gi. So here is where we use the invariant again to say that this edge is not in mx, therefore it must be in mv. Based on this, can you see what is the parity of j? We see that v0, v1 is in mx, and the path alternates between mx and mv, and the last edge is in mv. So that means that j must be even. So if we start from u going to v and then all the way up to vj, this has odd length. And we add this to gi to obtain gi plus 1. Now that we have constructed gi plus 1, we still need to make sure that the invariant holds for the new graph. Can you see why that is? We see that all the new vertices on the path are covered by mx, and their incident edges in mx are on the path. So no edge of mx can be in the cut induced by the vertices of gi plus 1. So the invariant holds for gi plus 1. And this completes our construction. And we obtained an odd closed-ear decomposition of G. And that completes our proof. And that also completes this lecture.